Hello, this is chapter 55, Manual Transmission Fundamentals. So, quick overview. Why do cars need different gear ratios? We'll talk about the history a little bit. There's a video that I'll share separately outside of this particular presentation. Talk about lubrication a little bit. In the classroom, I had a little bit of really simple hands-on. I made some Lego gear sets, and I'll talk about those a little bit when we get into actual gear ratios. Lab time, um, overall lecture and lab took more than the 1 hour I had for a Monday class, so hopefully we can get some hands-on time later. All right, so why do we need different gear ratios? If you've ever ridden a bike, you might have played around with how slow you can ride. And you know that as you slow down, things get awkward when you're trying to pedal the bike. And eventually you get to the point where you can't really keep a fluid movement going on with the pedals and everything. Gasoline, well, piston type engines or internal combustion engines, that's the ICE, they have similar phenomena. You've got a restricted mechanical movement going on there, and there's a certain range where it works great, but below that range or above that range, it doesn't work well. So just like pedaling a bike, you start to go really slow and you lose that fluid movement and you can't make consistent power and you end up stalling out. At the other end of that spectrum, you get going really, really fast. And on a bicycle, you may get to a point where you just simply can't keep your feet on the pedals anymore. And it's kind of like that with internal combustion engines, specifically piston engines. You start spinning them really, really fast, and eventually you get to a point where connecting rods don't want to stay attached to crankshafts anymore. Usually that ends in quite a spectacular failure. Um, but they all have this power range here. The green line is the torque. This is the twisting force that the engine can apply to the drivetrain. And you can see that it's fairly flat on this graph between 2,500 and 3,500 RPM. That's the real sweet spot right there on your tachometer where you can pull really hard and then maybe get to just a little bit past 3,500 RPM, then you want to shift. Anything more than that, and the torque starts to roll off really, really quickly up till 5,500 RPM on this engine. It gets down to where it's almost not usable anymore. So we've got this little range, and we want to take off in first gear, get the engine up to this speed. It'll accelerate nice. And then somewhere up here, we want to shift into second gear. So that'll put our engine RPM back down low, and we'll have all this torque to accelerate in second gear and keep going up through the gears until we get to cruising speed. Pros and cons of running slow and running fast. Oh, I forgot a space. So when you're running slow, you have very little power. If you've ever driven a manual transmission car and you're going slow and a higher speed, it does what's known as lugging. So the engine is moving so slow, it's like you riding a bicycle really, really slow. If you try to accelerate, you just can't. There's nothing there. So you have very low power available, and you can't accelerate at all. So that's these two things. If your engine is turning really, really slow, you're not giving a lot of energy into the water pump and the alternator. So you might not be able to move the coolant around to keep the engine cool. You might not be charging the electrical system. You may end up drawing down on the battery a little bit. There's also a vibration factor at play that this kind of goes in with the lugging thing. If you're turning an engine at really low RPM, the counterbalance weights and everything are intended to run at a certain RPM range. And if you're outside that RPM range, the counterbalance weights will not be as effective. And the vibration that you could experience could cause damage to the engine. At the other end of that, going too fast you're putting a lot of strain on the rotating parts. Remember, pedaling fast, it's hard to keep your feet on the crank. Same thing with the engine, pedaling fast and things come apart. Um, revving your engine at high speeds, it tends to lead to poor fuel economy. There's a sweet spot where piston speed relates to good fuel economy, and outside of that, you're not burning fuel effectively, and that's why graphs like this, they have this high point right here. This is where this engine is really good at turning fuel and air into kinetic motion. And then beyond that, it's maybe it doesn't have enough time to burn all the fuel and a lot of it's being burnt in the exhaust system or something, but it's becoming less and less efficient at turning fuel into kinetic motion down here. Another problem is cavitation or foaming of fluids. Cavitation is if you ever play in a pool or a lake or a river or whatever, and you splash the water, it creates a lot of air bubbles in the water. That's cavitation. Whenever you move water or any liquid really quickly, all these little air bubbles pop up, and they seem to pop up from almost nowhere sometimes. If you ever watch a video of a boat propeller underwater, the propeller is underwater for weeks, months, years at a time. Like I'm picturing movies where I've seen submarines that are under the water, and the propeller has been down under the water for a long time, but when it starts going really fast, it makes this little trail of air bubbles. That's cavitation. The air bubbles seem to appear from nowhere. The air was already in there, and the propeller is just whipping the air bubbles together into big bubbles. Anyway, that's cavitation. Air bubbles are not good in the fluid systems of your engine. So coolant, oil in your transmission has, especially an automatic transmission, it depends on a hydraulic fluid. Power steering, even your fuel system. If your injectors are opening and closing very quickly, you'll get air bubbles in the fuel system. And then you're injecting fuel and air when you're supposed to be injecting just fuel. So that could cause a lean condition. So cavitation is not great. And it's the main reason why engines can't rev high for extended periods of time. It takes a lot of effort on race car teams to make the engine survive at high RPMs. Your typical car engine could rev 2,000, 3,000 RPM for hours at a time. And that's fine because that's what it's designed to do. You start revving it faster than that, say 4,000 or 5,000 RPM, and it might only last for a few minutes, like 15 to 20 minutes at 5,000 RPM before the cavitation of oil and coolant catch up to you and cause things to overheat or not get enough lubrication. And if you keep going beyond that, the problems become exponential. If you take a standard automotive engine and you rev it to 8 or 10,000 RPM, it will only last a few seconds before the cavitation of the fluids, the coolant and the oil specifically, becomes so great that the engine basically acts like it's not being lubricated at all and immediately dies. So yeah, higher RPMs, when you're really, really pushing it, they can lead to damage because you got fluid breakdowns with your cooling and lubrication system. All right, going into the history of transmissions a little bit, Mr. George Selden, he had the first patent for a changeable gear ratio drivetrain in a motor vehicle. We don't hear about Selden much because he went toe-to-toe with Mr. Henry Ford in the court system over this patent. And well, I'm sure you've heard of Ford and you haven't heard of Selden. So that kind of tells you how that legal case went. He's got an interesting thing. He's got a little 3-cylinder front engine, front wheel drive car here. It's basically like the rest of the wagon is very similar to the horse-drawn wagons back in the late 1800s, but he just made this little front wheel drive transaxle and slapped it up in there, which is kind of cool. Um, but you could see some gears, a gear reduction over here on the side. But inside of this metal drum here is one belt, excuse me, one belt and two pairs of pulleys. And you had one pulley ratio that was made for cruising along, and this thing topped out at a crazy speed of 20 miles an hour. I think actually driving this contraption at 20 miles an hour would be kind of exciting. um, but if you needed more torque, you could stop the car. You could remove this cover right here and slide the belt over to an underdrive ratio set of pulleys. And then it would top out at just a couple miles an hour, a slow walking speed, but it would have a lot of torque. So then you could climb up ramps, hills, um, go off-roading with this thing because there weren't a lot of great roads when this car was made. So sometimes you needed that torque, but it required you to stop, get down on the ground here and get some tools out and change stuff around. So it was good that you had that option, but it wasn't the most ideal thing since you had to stop the vehicle. The next evolution, Misters Panhard and Lavoisier, they invented a sliding mesh transmission in 1894. And the car had an actual clutch pedal, and then you had a lever that would move gears around. So this gear set that you see on top, this is the output of the transmission, and this is leading towards the axle right here. This is a differential set. And the sliding gears were these gears way, way, way down here. And the way this worked, you have a small gear on this shaft down here that would mesh with this one up here. See this gap that's between this biggest gear and the middle gear here? These gaps were here for a reason. So this bottom shaft would slide over just a little bit, and this gear would mesh with this gear. And that could be your first gear. Then it would slide over a little more, and this medium gear on the bottom shaft would mesh with the medium gear on the top shaft. While it's doing that, this gear slides past, and so you're only in one gear ratio. You can't have a transmission in two gears at the same time. That would break things. So yeah, you continue moving this over, and this middle gear slides into this gap, and this biggest gear on the bottom shaft will mesh with the smallest gear on the top shaft. So that's how you change your ratios in this car. It was said that you could shift on the move with this, but since you're sliding these whole gear ratios, I don't know if you ever take your fingers and fan out your fingers and interlace your fingers in front of you, kind of like gear teeth, right? Now, slide them sideways like these gears would be, and then try to slide them back and see how often you can get your fingers to mesh like gears versus your fingers crash into each other. And like you can imagine the teeth on this gear crashing into the other teeth on this other gear while trying to mesh it. It took a bit of luck and practice to be able to shift on the move without creating a terrible gear gnashing noise on this thing. But it was a step up because you didn't have to stop the car necessarily. You could press the clutch, move the lever, and if you did everything right, you could be in the next gear and keep on driving. So in 1928, Cadillac invented the synchro mesh transmission. It wasn't quite like what the picture is here. This is a more modern type synchronizer setup, but it was the right kind of idea. So Cadillac figured out that moving the gears back and forth like this was a bad idea because you were literally grinding gears if you made that gear gnashing sound. And you grind your gears, eventually you strip the teeth off and you have no gears left, right? So that's bad. Um, but what they've come up with is this constant gear mesh idea where the gears are always meshed with their companion gear. And see that this gear has this smooth inner diameter on it. So it slides onto a shaft and it's able to spin freely on the shaft. That way, all of our gears can be meshed, and gears can be turning at different speed, but because they're basically just rolling along on the axle shaft, that's okay. To actually engage the gear, you have this hub, and you see it's got some splines on it. So the hub splines onto the shaft that the gears are assembled onto, and this hub has the sleeve that splines onto it. So you got the hub splined to the shaft, the sleeve splined to the hub, and they all rotate at the same time. The sleeve, by the way, this groove on here is where your shifter fork engages that thing and can move back and forth. So when you're selecting the gear, the sleeve will slide back and forth on this hub, and it will catch. You can see on this gear, it's got these little really small teeth on it. So when this sleeve were to slide back, it would catch on this and engage, locking that together. It would lock this gear with this sleeve to this hub, and it would transfer the torque through all of that into these splines to directly control the rotation of that shaft. So when you're shifting a transmission now, if you're grinding the gears, you're really not grinding the gears anymore. You're grinding the sleeve against these little teeth right here. That's what's being ground up. I got a list of developments here. Borg Warner figured out the modern type cone style synchro. That's these green cones right here. They figured that out in the 60s. And that's the way modern manual transmissions, if you have a manual transmission in your car, it's essentially works exactly the same. So it's been working for 60 years now, because yeah, 2020, yeah, 60 years now. It's been working the same way. We've kind of reached a point where they can't make it any better than it already is. All right, so here's that video. I talked about shifter forks. Here's these right here related to the shifter. The video does a good job explaining how the gears and synchros and everything work. What it doesn't talk much about is the shifter, the rails, and the forks themselves. So the rails, you got one, two, there's a third rail here. This is fifth and reverse fork right here, and it sneaks around over to the other side, and there's these three pockets down here. So in your manual transmission, you've got this kind of H pattern for first and second, or above and below each other. And then over a little bit, you have third and fourth. You can kind of see the demonstration up here. So when you're moving the shifter left or right, you're selecting which pocket the end of the shift lever is engaged in. And then when you move it forward or backward, you're moving that particular rail. So this short rail over here goes all the way over to this side. This is supposed to represent the first, second gear fork right here. This one right here, the long shift rail, this is the 3-4 one. So these are gears 3 and 4 right here. And then all the way over, this would be fifth and reverse on this one. Reverse is not yet on this thumbnail, but I'll let you watch this video after, well, if you choose to, you can watch it after this little lecture.
Manual transmission.
I didn't mean to do that. I'm sorry. Okay. Lubrication for manual transmissions. Some of them want a gear lube. Some of them actually want automatic transmission fluid. It just depends. You have to read the owner's manual. Some don't care. We have a Honda transmission in the classroom. The owner's manual said to use Honda's manual transmission fluid, which was really just a gear lube. I think it was a 80 weight or 90 weight gear lube. And we talked about weights when we talked about motor oil a little bit. So if you remember some of the numbers we talked about with motor oil, we had 5W30, 20W50, all these 80 weight and 90 weight. It's just a more viscous petroleum-based fluid typically. So some transmissions use that. Some like automatic transmission fluid just because its cold temperature properties make it a little bit easier to shift. The transmission that's in my little red car, is one of those where you could either use gear lube or automatic transmission fluid. And it says that if you live in a colder climate, it recommends that you use automatic transmission fluid. I think mine currently has gear lube in it right now because on really cold mornings, it's hard to shift my transmission. Things just don't want to move in there until it warms up. Anyway, to the point of changing the fluid on these things, it's very, very, very simple. On this particular transmission, this is a known as a T5. It can be found in Mustangs, Camaros that are from the 90s, also S10, Chevy S10 pickups. It was a really, really common transmission. It's a pretty good one. But you've got a drain plug that's down at the bottom here. So if you want to change the fluid, you get a pan, you pull the drain plug out, and it's a little square drive, so like a 3/8 ratchet would snap right in there. You can spin that plug out, you drain all the fluid out, clean up the threads on this plug, maybe put some thread sealant on it, thread it back in there. Then you got the fill plug. So there's no dipstick on here at all. The idea of the fill plug is you take your bottle of lubrication, whatever you're using, gear lube or automatic transmission fluid. You could use small bottles that you just tip up, or you could use a pump in the bottle, like a hand soap dispenser type pump with a hose attached. And you pump the fluid into the transmission until it starts to come out this hole. Once it starts to come out that hole, it's full. It doesn't need any more. And so you let it level off even with that hole. Then you put that fill plug in and you're done. No problem. Some transmissions, the reason why I chose this illustration is over here on the side, there's a reverse arm pin. This is a steel pin that goes into this aluminum case from the outside. This one's got the circlip on it, which helps a little bit, but that steel pin is threaded to the aluminum case, and it's different. You see how these are the square female drive on here for your ratchet? The one on the other side, they made it really tough. It's a tamper-resistant Torx bit. If you don't know what that is, it's because it's not that common. But the issue is some people assumed that seeing that that bolt coming through the side, that was the fill plug, and they would take that bolt out. This arm right here holds the reverse idler gear. If you take that bolt out, this arm falls down into the bottom of the transmission and jams up the gears. You lose reverse, you damage your gears, and the only way to fix it is to totally disassemble your transmission like this to get down there and put this thing back together. There's no other way to put it back together when it's installed in the car. So that was one downside to these transmissions, is if you weren't familiar, you might break your transmission trying to add oil to it. So you got to make sure you know which plug is your drain and which is your fill, and don't accidentally disassemble your transmission while you're doing it. All right, the Lego gears. I had these in the classroom. I passed them around a little bit, but I can talk to them a little bit right here. So these gray gears here, each one of these gears have 16 teeth on them. And I had these crank handles right here. Here's a little red handle, a little black crank arm. You could put it on that axle shaft, spin this gear, and this was a driving gear, and this would be the driven gear. A very subtle difference in the terms of those gears. But since they're both 16 teeth, every turn you give this axle shaft results in one turn on that axle shaft. That's pretty straightforward, right? So one turn to one turn, that'd be a 1-to-1 ratio. That's what we got going on the top here. In the middle of these things, I have a black 12th tooth gear and a tan 20 tooth gear. So one turn on the 12th tooth gear did not equal one turn on the 20 tooth gear. You can see the ratio in the middle here. That's the number of teeth, 12 to 20. This is the equivalent ratio. It would actually take 5 turns of the black gear to equal 3 turns of the tan gear. That's if we're going for whole numbers. If we're just looking for one turn of the black gear, it resulted in 6/10 of a turn of the tan gear. So hopefully you're following along that one turn on the small black gear was less than a turn on the tan gear. Moving down my little apparatus here, we have a small gray tooth, gray gear, excuse me, with 8 teeth on it, and then a big white gear with 24. How many times does 8 go into 24? 3 times, right? So it would take 3 turns of that little gear to create 1 full turn of this big gear. So I got that ratio spelled out right here. Now, all of these ratios are known as non-hunting ratios. If on the 16 tooth gear set, if one of these teeth, if I mark that one with a Sharpie and its companion tooth, I mark that one with a Sharpie, every time I turned that, those 2 teeth would always line up with each other every single time. On this 8 and 24, if I marked 1 tooth on the 8, it would line up with 3 specific teeth on the big white one, because 8 goes in the 24 3 times, right? So I could take a Sharpie and I could mark 3 teeth on here that were spaced out evenly, and that 1 tooth on the small gear would line up every single time. This is important because all modern transmissions go with a hunting gear ratio. This gear, if this tooth that I marked was damaged, then it would start to damage its companion tooth. And in the case of this 1-to-1 ratio, if this 1 tooth here, let me see if I could annotate this a little bit. So if this tooth here was broken, it would start to cause problems for this tooth right here. And every time it goes around, those 2 damaged teeth would keep hitting each other and keep damaging each other. It's like bad teeth in your mouth. If you got 1 tooth that's out of place, it causes pain every time it hits other teeth, right? So if you had 1 little piece of damage, 1 nick, scratch, or chip on that tooth, it would wear out this other tooth really bad, really quickly. And before you know it, you've got 2 missing teeth altogether there. And that's not good for gears, not good at all. Now on this one over here, let me see if I can find a clear one. We got these teeth are meshed right there. And if I count 1, 2, 3, 4, 5, 6, 7, 8, that tooth on the little gear would come around and it would hit this tooth here. It would hit that one, then that one, then 1, 2, 3, 4, 5, 6, 7, 8. It's kind of outside a little bit, but it'd be down on the bottom. It'd be a triangle, right? So this bad tooth on here would hit 3 different companion teeth on this gear, and it would cause problems, but it would be distributing the damage that it causes. So it would take longer to get to a catastrophic point on there. That makes the gears last longer. They can be more tolerant to damage and they last longer that way when you have when you're not repeating the companions like you are on this 1-to-1. Modern gears, you'll find something like a small gear with 10 teeth on it. I'm not going to draw all 10. I'll just write 10 in here, right? All right, and then a big gear that has a weird number like 41. So picture this one has 41 teeth on it, and this one has 10. So how many rotations of the 10 tooth gear does it take to equal 1 rotation of this one? Well, 10 goes into 41 4.1 times, right? Click the wrong button. Darn it. Anyway, so yeah, 4.1 times is how much it would take to make it work. I got my pen back. 4.1. There we go. All right. So if this tooth right here were bad, it would mesh into these 2 teeth and it could damage those teeth. But it would take 41 rotations of this tooth to mesh up with these 2 teeth again, right there. and cause the wear to affect those two teeth again. So what that's saying is this hunting ratio where it's not a whole number, like these ones down here are whole numbers, 1 to 1, 3 to 5, 1 to 3. These teeth are going to meet their companion teeth really often. This one with the hunting ratio, this tooth doesn't meet its companion teeth as often. It's going around and it'll hit one over here, and then one over here, and then one over here, and one over here, and one over here, and one over here, here. And because this isn't a whole number, it won't hit these teeth again. It'll hit some teeth next to it, and it'll keep going around and distribute that wear out across the whole thing. And the idea here, what happens in practice is that having one bad tooth mesh with all these other healthy teeth, it hammers out the problems on that one bad tooth and it makes it better again. It's kind of like if you're not feeling great and you hang out with a bunch of friends that can help you out emotionally and everything, it kind of restores your health a little bit, right? So you can kind of think of that with this hunting type gear ratio. One bad tooth, when it meshes with all these other good teeth, it kind of hammers it back into shape and keeps it healthy so it can keep running for a long time. And it also distributes that little bit of wear out across all of these so that you're not damaging one a lot. You're damaging all of them so little that it might not even matter. They're built to handle it. All right, let me see if I can turn my annotations off. Oh, they're still there. Son of a. Okay, come on. Annotations and clear. Clear all my drawings. Yeah. Now close. All right, so went into the lab time and started working on transmissions. Two notes here. On the lab sheet, there's a question about a reverse switch on a Honda transmission. We don't have that switch in the classroom. We're missing that part of the transmission, so you can ignore that switch, that question about the switch. Second, I just wanted to highlight that we talk about how many speeds a transmission has. It takes 2 gears to make a gear ratio, right? So we've got these 2 gears right here. This is 1 speed. These 2 gears here, this is a 2nd speed. We got a total of 4 gears here, and that equates to 2 speeds total on here. So when I'm asking questions, how many speeds is a transmission? You don't want to just count on the gears. If you see 8 gears in a transmission, that doesn't mean it's an 8-speed transmission. That probably means it's a 4-speed transmission or a 5-speed transmission. I'll let you watch the video and you can see how 8 gears can translate into 5 speeds. Anyway, thank you.